Mm. Good evening, everyone. Okay, good afternoon. Fine, let's start. Most of you are already here with us. You have joined, so good afternoon. Okay, so yesterday we were વાંધો નહીં વંદન સ્કૂલ ચાલુ થવા દેજો હું તને બોર્ડ ઉપર ડ્રો કરવા બોલાવું પછી આવજે. Okay, so we discussed two properties of electrostatics so far. The first one, okay, where is that? Yeah, is here, right? It is that in electrostatics, inside the conductor body, the net field is zero, right? Okay, and whenever we say electrostatics, it means when everything has come into equilibrium and charges are stationary, right? Okay, so that's the idea, right? Then the second property is over here, that this one, right? In electrostatics, the charge given to a conductor only stays on its surface, outer surface, right? That is, there is no charge anywhere inside the body, right? Okay, you can also write this again as there is no charge, no excess or extra charge anywhere inside the body of conductor. Again, this sentence only applicable for electrostatics. Next chapter માં આ બધું ખોટું પડી જશે. Okay. Right? Okay, this has gone crazy. It says that there are only 15 people in the meeting. Now, we are going to the third property, right? Okay, the third property is what I was actually trying to explain it to you earlier, right? But anyways, now we'll go to that, and I'm going to call it 3, right? Again, the order or the number is not important. It's okay. You can write them in any order you want, all right? So this is the third property that we are going to talk about today. It is that electric field at the surface of conductor is normal or perpendicular to the surface at every point. And of course, this sentence is true for electrostatics, right? So what does this sentence mean? That suppose you would give some charge to this sphere, right? Let's say a sphere, all right? Okay, this is what we have already proved. Charge is only at the surface. Okay, so that we are not going to worry about now. So I've shown some charge in this diagram, right? I've, I've, I've shown some charge, right? And we are going to prove that all the electric field at the surface is normal to the conductor. Normal means perpendicular. So we are going to prove that it should be like this, right? Perpendicular to the surface, right? That's what we have to prove, or that's what this property is about, right? Okay, like this. Okay, I'm assuming charge is everywhere, right? So how do we prove it, or how do we understand it? Well, listen to this carefully. It is that if you will consider, suppose that this is the surface, right? I've zoomed into it, all right? Okay, and this is the surface, and here is, let's say, some tiny electron at the surface, all right? And let's say that the electric field, let's say that the electric field at this point is, suppose, not normal, all right? Let's say it's at an angle like this, right? We are assuming, okay, this diagram is showing what we are assuming, all right? So let's assume that here the electric field is not perpendicular to the surface, all right, but it's like this. Then what will happen? Then I can say that for this electron, this electric field can be considered to be in two components. One, parallel to the surface, means tangential to the surface. I'm writing that as ET. ET, T for tangential. And another, normal to the surface, EN. All right? Have you understood? ET and EN are components. Whose component? Of E vector. Right? Okay? So then, obviously, due to En, think about En, right? Due to En, this electron will get a force in this direction, right? But I'm sure you all remember that because of the whole material of the, due to the whole chemistry of that whole material, right? It's not possible that electrons can go out. So this force is going to get cancelled, all right, by some other forces. But this ET will apply a force on this electron in this side, right? Okay, I know I made a mess of the diagram. I'm so sorry. Let me erase all these things, right? So what I'm saying is that because of this ET, there will be a force on this electron in this direction, right? But there is nothing to cancel that force, right? There is nothing to cancel that force, right? So what will happen is that this electron will start sliding or moving towards this side, because if there is some particle and some force is applied on it and there is no cancelling force, this particle cannot remain stationary. So the electron cannot remain stationary. Did you understand this? Yes or no? I'm waiting for you. Yes or no? Okay. In such a case, should we call it electrostatics? What about electrostatics? Electrostatics means we are considering the case where charges remain when charges remain stationary, right? We are considering the case where charges remain stationary, right? But here we are getting opposite. This is wrong. Okay, so that means what we assumed. So that means what we assumed is wrong. Okay, yeah, fine. I'll explain it on new diagram, right? Again, very quickly, this is the surface, right? Okay, and the electric field has two components. Suppose, right, like this. Okay, then because of this field, this component, the electron will start moving, okay, in parallel to the surface like this, right? So this electron will go that way, but we are assuming that everything should remain stationary, so this is wrong. Okay, so the assumption must be wrong, right? What did we assume? What did we assume? We assumed that the electric field is at an angle like this, right? That's what we assumed. So it must be wrong. Instead, what we should have, right? What we should have is that ET is equal to 0, yes or no, right? Purvendra, any problems now? Chaitya, I hope you understood. Right? Now if ET is 0, then what is remaining is only En, correct? Right? It means electric field is only normal to surface. All right? I hope you have understood how we got that. Okay, now this is going to happen at every point, right? Okay, this is going to happen at every point. So even here or here or here or here. So everywhere the electric field will be making 90-degree with this. Is that fine? Okay, right? So we have studied three things now, right? First, inside the body there is no electric field, right? Inside body of conductor there is no electric field. Second, at the surface the electric field is normal to surface, right? Okay, and third is that inside the body or in the body of conductor there is no charge, right? All the charge is on the outer surface, right? The charge is only on the surface, it cannot be in the body, right? Okay, right, so those are the three properties. Now based on this we are going to the next property. All right, so property is that in electrostatics, every point in the body of conductor has same potential as the surface. Okay, right? In electrostatics, every point in the body of conductor has same potential as the surface, right? So what does this mean? Let's say that this is some conductor. Okay, let's say that this is some conductor, right? And this is solid. Right now we are talking about solid. We'll talk about what happens if it's hollow, because then it's a bit of tricky case. Let's say this is solid and we have given it some charge, right? Let's say we have given it some charge, positive charge. So where will the charge be if we give it some charge? If we give it some positive charge, where will the charge be? Where will the charge be? I've started to get some correct answers. Okay, yeah. Okay. Outside, yes. On the outside surface, right? Okay, very good. So plus, plus, plus over here, right? All on the outside surface, right? Okay. Now, at all these points inside over here, everywhere, this electric field inside everywhere is going to be zero. Yes? Okay. Electric field inside is going to be zero, right? That's one more property that we have proven, right? Okay. Now, I want all of you to think of this relation. Oh, sorry. Right? Is that okay? Now, do you realize that suppose I go from point A to B, then anywhere in between there is no electric field, right? Okay, anywhere between A and B there is no electric field. That means dV is going to be zero. Understood? Yes, no. What do you say? I said that if you go from A to B, right, anywhere inside this, right, A to B, then there is no electric field at any point. So dV, which is given by this formula, is zero, right? Because E is zero. Zero no dot product or the zero जाते, right? Okay. So now dV is zero. What is meaning of dV? Change in potential, right? Correct? Change in potential. But the potential is not changing. So do you agree that VA is equal to VB? Correct? Also, if you consider that suppose instead of taking B here, right? Oh, just a minute. Suppose we take one point A over here and we take one point B over here, right? On the surface. Where is B? B is on the surface, right? Now, okay, still the same logic holds because electric field is not on the inside. It will start from here. I hope you understood what I'm saying. The field lines will start from surface, right? Field lines will start from surface. So if you go from A to B, anywhere in between, E is going to be still 0. Clear? This second case is clear, yes or no? This is different from the first one, right? How is it different? In the first one, I took B and A both inside. Now I'm taking A inside, but B is on the surface, right? Still the same logic will work, right? Because anywhere in between, no, Krupa, that's not correct. Anywhere in between uh, A and B, still there is no electric field. I am not saying VB is 0, Purvendra. Have I written anywhere that VB is equal to 0? Where did I mention that VB is 0? Can you read it anywhere here? Okay, Purvendra, VB is not 0. Right? So, still VA is equal to VB. So, based on this, do you understand that I can write this? V in the body is equal to V at surface, because B is at the surface and A is in the body. Understood? If yes, please say it so then we can continue. At B, there is electric field. Okay, good question. Fine. Joy, what is not clear? If no, can you please type your question? Okay. Right. Fine. It's working now. So first I'll answer Purvendra's question. He's asking that suppose this is the point B, then the electric field is starting from B, right? Okay, I hope Purvendra you understand that. Right? Okay, Joy, I'll come to your point also. And this is suppose the whole body, right? And some point A is inside that body, right? Okay, so A is definitely in the body, right? This is a solid thing, okay? I'm not talking about hollow, right? So then displacement vectors, small displacement vectors may be like this, right? You can go on any path, right? Let's say I choose this path, then I'm going to stop right over here, correct? So wherever dr vector is, right, it's always only up to the surface, right, on the inside. Okay, it is on the inside and only up to the surface. But electric field is 0 everywhere for such cases, only above the surface. Above, that is starting from surface and going forward, right? Starting and above the surface, right? Only in this point electric field is not 0. So because we are coming from the inside and we are only going up to the surface, that's why E vector dot dr vector will always be 0. Okay. What if there is electric field at the surface? Manav, that's exactly what I'm explaining. Right? The electric field is at the surface and then it starts, okay, in the outward direction, not inward. अरे शायद नहीं मानव, right? What we are studying here, they are actually, these things are like laws. Okay, you cannot say if there is electric field at surface, right? Electric field only starts from the surface and it is above the surface, not below or not under the surface, right? Okay, now to answer Joy's question. Uh, Joy said, how is V inside equal to V at the surface? Joy, I'm saying that this point A is inside, right? And this point B is on the surface. And I hope you understood that we got VA is equal to VB, right? Because E vector dot dr vector is 0. All right? Is that good so far? Okay. Then A could be any point inside, right? A point is not special. I could have taken A point here and then we could move like this, and then come here. Still, we would have VA equal to VB. So what I'm saying is every point inside this body, every point inside the body. See, when I say body, it means I'm talking about the solid part, all right? We are not talking about hollow. Hollow deserves a special mention, right? So we'll talk about that at last. So everywhere inside the body, VA potential at A is same everywhere inside the body, right? So that's why VA is equal to VB, and for VA I can write potential inside, right? For VA I can put potential inside, and for VB I can put potential at surface, all right? So that's how I'm saying that potential inside and the surface is same. All right, Purvendra. No, Jay, no. VA is equal to VB. I'm not saying this is equal to 0. એવું મેં ક્યાંય લખ્યું જ નથી. I'm not saying this is equal to 0. Correct. Krupa, correct. That's right. Okay, Purvendra, but third at B, there is EF. Then E can't be 0 for B. Of course, I'm not saying E is 0 for B. I am not saying that E is 0 for B. Right? What I am saying is we are doing this integration only up to B. And electric dr vector last dr vector અહીં આવશે અને first જે electric field ચાલુ થાય છે એ આમ થાય છે, right? So there is no common point, there is no common point for them, right? એવો એકય point નથી where there is dr vector and where there is E vector also, right? Okay, Jay, now to answer your question again. Jay is asking a very good question which I'm going to pass on to everyone. He is saying inside the body electric field is 0, and I agree, right? This is a conductor, so inside body of conductor electric field is 0 because we are talking about electrostatics. Then is V equal to 0? What do you think? Yes or no? What do you think? Come on. Okay. Many of you said no. All right. Some of you said yes. Okay. Okay. Right. Fine. So those who are saying no, can you give me a reason? I've got only one person's reason, and that reason is correct. No, Kia, that has nothing to do with scalar vector. So many of you have given me reason. Come on. Sorry. So many of you have said no. Can you please give me a reason for saying no? Okay. Well done, Purvendra. But Avinash, the question is, would not VB be 0? That's what people are concerned about. What if V is 0 everywhere? Okay, yeah, now that is valid. What you said is valid. Potential inside cannot be 0. Which was not necessary. It can be 0. Okay, Omdeep, well done. Correct reason. Yes, Avinash, that's right. Come on, people. Everyone else. Reasons. Uh, yes, Darshi, do you have a question? Okay. Yeah, no problem. V surface can't be zero. How can you say that, Vivek? Can you prove it? Well, the correct answer to this is maybe. You cannot guarantee, right? You cannot guarantee, but what you can guarantee is this. This is what you can guarantee, right? The reason is if you go back and look at what formula is dv, it's this, right? Okay, clear? So what this means is that change in potential is E vector dot dr vector, but if E vector itself is zero, so if E is zero, then V will be constant, right? This is actually a very important rule, everyone. You can remember this. Wherever electric field is zero, potential is constant, right? See, you can also roughly or loosely think about it like this, right? This might make more sense to you, right? Whose differentiation is zero? Whose differentiation is zero? Everyone. My differentiation is zero. Ah, yeah. Yes. So now I hope nobody has a doubt that because the inside electric field is zero, that's why inside potential is constant. Fine. Now I hope you will remember this. All right. Okay. In fact, uh, this is something that happens in shells and such things. All right, but we'll talk about that at a later time. Right now, I want you to remember this thing. Right? Okay. So read the sentence. Are you happy with this sentence now? Yes, Krupa, it's exactly like that. Sure, Joy, Purvendra, those who had questions, Manav. Okay, right? The easiest way to understand or to write it is, yes, Jay, I was going to come to that sentence. Right, Swarali, I'll answer your question as well very soon. Just a minute. So the easiest way to understand this is that inside the body electric field is zero, so potential should be constant, and this will happen only up to the surface, right? Once you go out of the surface, this will not be true, right? So that's why everywhere inside is same potential, and that same potential is also same as the surface. All right. Okay. Now, so first of all, yes, Codal, it is also possible that V is zero, but whatever it is constant, right? Okay. So now Swarali's question, should electric field outside be uniform? No, that has no connection with this, right? Outside, it could be anything. There could be a storm outside, but no problem, the electric field inside this body will be zero and the potential will be same everywhere, right? Actually, that reminds me, we should not use constant, we should use uniform, right? I hope you understood the change. Constant means does not change with time. Uniform means does not change with place, right? So uniform is actually a better word. No, it won't. See, it won't affect the potential like you are thinking, right? Let me just take a minute to explain this. Suppose you have got, suppose you have got this object, right, which is a solid conductor, all right? And let's say here somehow the potential is 50 volt, then it will be 50 volt everywhere inside, all right? That's what we have studied so far, right? Okay. Now if we suppose from outside put some external, take this object and put it inside an external field, let's say like this, all right? Then if we put it, if we put this conductor in external field, uniform non-uniform doesn't matter, all right? If we put this in external field, then potential at each point will change, right? Okay, and then it might happen that these charges will redistribute. અરે આ બાજુ ફીલ્ડ હોય ને તો આ પોઝિટિવ ચાર્જ ભાગી જશે, થોડાક આ બાજુ આવી જશે. I hope you understand what I'm saying, right? And finally in electrostatics, when everything is in equilibrium, what will happen is that the electric field everywhere here will become zero, right? Finally, and the potential will become same everywhere, right? But it will not be 50 anymore. It's possible that it might have changed, right? That will depend on field. How it will change, how potential will change will depend on this field. But because you are applying this field from outside, the potential will be different from 50 but same at every point. So possible that at every point now it is 60, right? At every point it is 60, right? I hope that is clear. All right. So before applying field, it was same everywhere, it was 50 everywhere, right? Everywhere inside, that is, okay, not outside. And after applying field, it will change, suppose, and it will become 60 everywhere, right? That is what will happen. It will increase or decrease depends on how you are applying field and what kind of field there is. If there is a point B outside conductor and point A on the surface of conductor, then electric field is same or not? No, not same. અરે આના તો બહુ બધા એક્ઝામ્પલ છે, માનો suppose this is a solid, this is a shell, right? Metal shell, okay, and it is charged. First chapter માં આવતું હતું, and here you take one point B and here you take one point A. તો બેનું field અલગ હોય ને. Electric field at B is K cube by small r square and electric field at A is K cube by capital R square. So these are different. તો એ રીતે અલગ જ આવે. All right, okay. So now that's it about this property, okay, that every point inside it and the surface has same potential, right? Only valid for conductors. પછી wood માટે નો વાપરતા, નહીતર એ જ wood થી મારવા પડશે. Now next question, next property, number 5. Actually that reminds me of what Joy said. Sorry, I was going to forget it. Let's write one more sentence before we go to the next one. હવે બુકમાં બુકમાં કયા ઓર્ડરમાં કેવી રીતે આપી જાય મને યાદ નથી, એટલે આપણે નંબર ઓછો વધુ થાય તો કમ્પ્લેન ન કરતા ખોટી. So here is that sentence that Joy was talking about. Surface of conductor is equipotential. Understood? Yes or no? શેલ ની વાત પછી અવિનાશ, શેલ ની વાત છેલ્લે રાખો, વધારે મજા આવશે. There are actually two reasons. One is this property itself, right? The other reason is this one. બરાબર ને? I hope you remember this one also, right? So because of that, I hope you remember that electric field is always perpendicular to the equipotential surface. So આ એના જેવું જ થયું, right? So that's why this is true, right? So this is an important sentence. Please remember it. એને સાદી ભાષામાં કેવું હોય તો શું કહેવાય? All points on conductor surface, all points on conductor surface are at equal potential. બરાબર ને? But don't forget, this is only valid for electrostatics. આ બધું વારે ઘડી યાદ કરવું પડે, નહીતર પછી તમે ગમે આ વાપરવા માંડો. ઓકે, right? So that's about this property. Let's go to next. The next property is about magnitude of electric field at or close to surface of conductor, right? That's this next property. I think it's number 5, is sigma by epsilon 0, right? એટલે વેક્ટર ફોર્મમાં લખો ને તો આવું થાય. ઓકે, લખવાની રહી ગઈ. I will show it to you at the end. All right, Aman, please remind me. Okay, I will show it to you at the end. So this is that next property. I hope this does not surprise you. This has already been explained. Okay. Oh, well, I'm thinking that we should change this sentence a little bit to make it perfect. I'm adding something here. I'm so sorry. You might have to write this whole sentence again. Okay, not over there, here. I will write it again anyway. Don't worry. I will write it again. Magnitude of electric field due to charge on conductor ના કઈ નહીં. Sorry, I got confused. બરાબર જ હતું. It is true in all cases. I'm so sorry everyone. This is true in all cases, right? એમાં કઈ વધુ લખવાની જરૂર નથી. I just did the derivation in my mind, okay, while writing that sentence. All right. this is okay, no need to change. Okay, so sorry, let's prove this, right? Let's prove this. See, suppose this is some randomly shaped surface, all right, gamme તેવો shape હોય વાંધો નહીં. What we are going to do is we are going to take one point that is very 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 close, infinitesimal ની વાત ચાલે છે. All right, we are going to talk about infinitesimally close point, right? તો આને zoom કરવું પડશે ને, તો zoom કરશો તો કેવું દેખાશે? Not zoom meeting, only zoom as in magnification. So if we zoom it, it's going to look like this. Here is the point P, and I want to find what's the electric field magnitude at P. Direction બધાને ખબર છે, normal, right? We all know that the direction is normal, right? So suppose this has a positive charge. Let's say that this surface has a positive charge, right? And in this region, the surface charge density sigma, all right? Okay, so what am I going to do? I will make a Gaussian surface, all right? I will make a Gaussian surface of what shape? Like a cylinder, but a small cylinder, આવું લાંબુ નહીં. Okay, not like this, a very short one. Okay, this is obviously short કારણ કે આ infinitesimal distance છે. This distance is very small, right? So this is a short cylinder, right? Such short cylinder is also called pillbox. Word યાદ ન રહે તો કઈ વાંધો નહીં, રોતા નહીં. Okay, this short cylinder is called pillbox. Short means very less in length, like a coin actually. You can think of it like a coin, right? So suppose this cylinder has surface area dA. Okay, this not total surface area, this surface area, all right? Okay, understood so far? Yes or no? I'm waiting for you. Have you understood that this red is a Gaussian surface? Its shape is like a cylinder. This flat surface area is dA. Now if we draw electric field, I'm assuming this is positive charge, so this electric field will come out normally. Is that okay? Like this. Clear? Diagram બગડી ગયો મને ખબર છે, ફરીવાર draw કરું છું. This is the electric field, right? Okay, and this is that cylinder, like this, all right? And pink is the surface, બરાબર ને? So now over here dA vector or area vector is also in the same direction. So for this Gaussian surface, if we use the Gauss law, right, then Gauss law says that phi is equal to sigma q and close divided by epsilon 0. But flux is, well, look here, for curved surface, see where's the curved surface of this cylinder? Of course this one, आज ये देखा है curved surface. For curved surface flux is 0 because electric field is going to be perpendicular to that area vector, right? Not this one, આને આપણે dA1 કહી દો. I'm talking about curved surface, all right? So let's call that curved surface 2. Did you understand this? I'm waiting for you. મને લાગે બહુ મોટું ડ્રો કરવું છે તો કદાચ ટપો પડે. આ કેના જેવું છે ખબર છે? ઓલી શીટ જેવું છે, રાઈટ? ફિગરમાં હો ખાલી, આન્સરમાં નહીં. Okay, yes, I will repeat. Right, see what I'm saying is that everywhere the electric field is perpendicular to this surface, right? Normal electric field હોય ને, one of the property of conductor, right? Now what happens here is if I take this curved surface area vector will come out like this, right, in these different directions. Okay, but every time electric field is like this and the small area vector of that curved surface will be like this, so the angle between those two will always be 90. આ બાજુ હોય ગમે હોય, right? 3D માં imagine કરવાનું છે. Okay, just a minute, everyone wait, I think I have some objects here, I could use those. Can you see the water bottle? Okay, so what I'm saying is that this pen, right, is like area vector. All right, so any curved surface છે ને, તો આમ ગમે ત્યાં draw કરો, right? Okay, maybe like this or like this or like this, right? But the electric field is like this pen. Can you see this black pen here? Right, electric field is along the cylinder axis, right? Electric field is along the cylinder axis, but this area vector is like this coming out. So I hope you realize that the angle between these two is 90 degree, and આમ ગમે ત્યાં ફેરવો same જ થાય, right? Is that okay? All right, remember this Gaussian surface is very tiny. Don't forget that this Gaussian surface is extremely small, infinitesimal, right? So you can actually say that this part is flat. આ જે part છે ને એને તમે nearly flat consider કરો તો ચાલે, right? Because it's so small, right? Okay, so again I said that for the curved surface the flux is 0, right? હવે કઈ બાકી રહી? આ 1 છે અને અહીંયા 3 છે, right? But for 3 means this. For 3 electric field is 0. Yes or no? No? Why is it 0? હા કેમ કરો છો? હે? No આવે હવે. Why is it 0? It comes outdoor. શું અવિનાશ? It comes outdoor? Why are only 6 out of 60 giving answers? બાકી બધા સુઈ ગયા? It is not 0, Jay. 0 તો બરાબર. Why is it 0? 90 degree angle નથી થતો. Okay, Sakshi, interesting answer. Theta is 180. Chaitya, this is the question. And why? Well, the correct answer is yes, it is 0. કારણ કે આ point તો અંદર છે ને conductor ની. Have a look at the diagram. Where's this point? This is inside the conductor, right? This is of course conductor's surface, right? So આ point આ બાજુ લો તો ઈ ક્યાં હોય? Surface થી અંદર છે ને? It is inside the conductor. Is that okay? સાંજે બધા સુઈ જાય છે, સાચી વાત છે. How many of you understood this? Because that is inside the conductor. 10 જણ નથી થયા હજી તો બોલો. Okay, I'm saying that at this point is of course inside the body of conductor, right? Because this is suppose the whole conductor, right? Okay, so where's this point? This is inside the conductor. So inside the conductor electric field is zero. આખું draw નથી કર્યું. કેટલા જણના આન્સર આવ્યા કહો? 13, 14. અરે બીજા લોકોને નો સમજાતું હોય તો કહેજો હો. Please don't hesitate. Everyone, yes, no, જે હોય, don't hesitate. ખાલી મને જ ખબર પડે છે. I am sure you can see that, right? You are only telling me, you're not telling anyone else. So your answers are not being made public. Don't worry. Okay, fine. So બસ હવે આનો એક છેલ્લો સ્ટેપ પૂરો કરી લે એટલે ડિરાઈવ થઈ જાય. સર બોથ સાઈડ કવર્ડ ઓર એટલે એ ગોસ લો વાંચીને આવ ચૈત્ય. Chaitya, read the rules of Gauss law, please. That will help you. Okay. See, electric field inside is zero, right? So now we have to only worry about surface 1. For surface 1. Of course, E vector and dA vector are in same direction, right? I'm sure you all can see that or notice that from the diagram, because electric field is also normal and this area vector is also normal, right? So that's why flux is going to be E into dA cos 0, but flux is equal to charge enclosed by epsilon 0. Whatever a Gauss law. For charge enclosed, how much charge is enclosed? Well, only this part, right? So sorry for this ugly diagram. Have a look here. Only this part is enclosed, right? અહીંયા જેટલો charge થઈ આવે ને, over here, whatever is the charge. So that charge is on the surface. So for that, I should be writing sigma into dA, because area of that part is dA. Sigma da, yeah, correct. Okay, area of that part is dA, and the the surface charge density is sigma, right? So if that's the cylinder, we only have to consider this area, so that is dA. So it will become sigma dA, right? So dA dA cancels, and sigma in magnitude is equal to, E in magnitude is equal to sigma by epsilon 0. But this electric field is at the surface. Don't forget that, right? Not inside. Inside is 0, right? So electric field at the surface, sigma by epsilon 0. Electric field inside the surface or in the body is 0, right? And direction normal, એ તો ખબર જ છે. ચલો બસ હવે પૂરું કરીએ. So I want all of you to go through this topic. All right. Okay, I want all of you to go through all this, right? હજી પૂરું નથી, હજી એક બાકી છે, right? I will take your doubts tomorrow. All right. I will take your doubts about all this tomorrow. Okay. So make sure you read it and you prepare something. Goodbye, everyone. Yeah, goodbye. મીટિંગ એન્ડ જ નથી થતી બોલો. બસ હવે અહીંયા જ રોકાઈ જાઓ. બે શું નાટક